Hi, and welcome to the University of New South Wales and the School of Mathematics and Statistics. My name is Thomas Britz, and I'll be looking at problem 51 in the course 3411. It's a rather long problem, and it's all about entropy, so there's a lot of calculations, and therefore I've written up some stuff on the board already. The basic problem, what it's about, a couple of useful identities, some notation there, and also what we're supposed to calculate in parts A and B out of the 4 parts. So the problem is about entropy in this system here that represents a noisy channel. The channel has 3 symbols as its source symbols, so they are the symbols that we can send through the channel. And at the other end, in the receiving end, we can receive these 3 channels here. So it's a bit more complicated than the usual channel that we'd look at, which is usually the binary channel. But it's not too bad because there's a lot of symmetry here. The conditional probabilities are given like this. I've drawn them in green and red. So the probability that we have one of these symbols and receive the symbol just across from it with a green edge there is a half. And all the other probabilities, conditional probabilities, are just a quarter. So for instance, the probability that we get B3, given that we sent A3, is a half, but the probability that we get B3, given that we sent A1, is just a quarter. So for this setup, for this channel, we have to calculate a number of entropies. The entropy of A, B, the entropy of B given A, and conversely, and the joint entropy and mutual information. So we have 2 sets of probabilities for the source, and then we can work out all of these numbers, and that's what we're going to do. Now, there is a shortcut, or there are a couple of shortcuts in fact. One of them is to calculate this conditional entropy here, the entropy of B given A, because we can use the symmetries here. So let's do that. The entropy of B given A is by definition the sum of conditional entropies of B given any of the symbols A times the probability that that symbol was sent in the first place. So now we don't know what those probabilities are, those P of AI. We've got some here, but they're different as you can see. We're going to calculate this sum regardless of the value of P of AI. Now the way that we do that is that we look at this entropy here. So the entropy of B given some symbol AI, that's equal to the sum of probabilities, conditional probabilities that we get some Bj given AI, times the logarithm, and now everything is binary, times the same probability, Bj given AI, and we need a little minus in front. Now, these conditional probabilities, they are the same regardless of our Bj's. The order is just, Bj and AI, the order is just different. So for any given AI, for instance A1, then we'll have that one of these probabilities is a half, the green line, and the other 2 are red. So we'll have that this is equal to minus a half times log a half minus a quarter log a quarter, and then another minus a quarter log a quarter, and that's a half, a half, a half. That's equal to 3 halves. So regardless of which symbol was sent, which of these AIs was sent, the entropy of B, given that that symbol was sent, is just 1.5. So if we insert this up here, then we have that this conditional entropy there is just 3 halves, and then we have the probabilities of AI there, and that's equal to 3 halves times the sum of probabilities of AI, which of course has to add up to 1, regardless of what they are. So therefore we get that this entropy here, B given A, is just 3 halves. So So let's write that down. So 3 halves, or 1.5 if you want. So 3 halves down here, 1.5. So we've filled out a little bit in this table. Not a lot, but it's an important fact that we'll carry through the exercise. So let's now look at some of the actual numbers related to the probabilities that we're given. For instance, if we look at these probabilities here, the probability that we have A, 1, 2 and 3, we're sending them with probabilities a third each. Well, what's the entropy of A then? Well, that's just the sum of this minus minus the probabilities of AI times the log of AI, or in this case, minus a third times the logarithm of a third, and we've got 3 terms, so this is just equal to 3 times this, and this cancels out, gives you minus the logarithm of a third, or in other words, the logarithm of 3, which is roughly around about 1.585. So that's the entropy of A. So let's write that down, 1.585. Okay. Now, I've got this notation here that we can use, and that, if you see this function here, the information of x, that's given by minus x times the logarithm of x. So what we really have here in the entropy is also what we could get by writing it this way. So the minus disappears, and then we just have a sum over I of the AIs. That's a bit more compact. We don't really need it right now, but we will need it later to make things more manageable in our notation. Okay, so let's use this number now. We've got the entropy of A, we've got the entropy of B given A, so we can calculate, for instance, the joint entropy. So we've got A, B there, the joint entropy of A and B. That's the entropy of A plus the entropy of B given A, the entropy, so to speak, of B without the newsworthy bit of A, if you want. And that's just those two numbers here. So 1.585 plus 1.5. So that gives you 3.085, and now writing a little awkwardly there, 3.085, and then we have another number in this table. So, to get more numbers in the top row, let's look at the entropy of B. So that's equal to the, well, again, the sum of these probabilities BI, if you want, or P of BI. Before I wrote just AI, maybe that was a little bit confusing, but anyway, or to write it up explicitly, we've got that's minus the probability of any BI times the logarithm of that probability. Okay, so we need to find the probabilities of each of those BIs, so let's do that. So we've got P of BI. Now, we could look at them individually, but again, there's symmetry in part A at least. So the symmetry here is that we can calculate BI as follows. We take the probability that we get BI given that we sent some AJ Yeah, now I've confused I and j, but that's okay. And multiply that by the probability of getting aj, and there you go. Now, again, in this case, the probabilities are the same for all a's. So this is equal to just p of b I given aj times a third. And that gives you then, if we put the third over here, that we're just adding up the probabilities for each of these here. So the probability of getting bi, given that we came from each of these three. So one of these terms is going to be a half. The other is going to be a quarter, and finally we have a quarter as well. So this just equals 1, and we're left with a third. So apparently, because of all this symmetry, we get that the probabilities of the bi are just equal to a third. So it's all very symmetric. So here we get, again, these are equal to a third here. So it's exactly the same as in the entropy of A case. So the entropy of B is going to be the same because the probabilities of the symbols in B are the same as in A. So we end up with the logarithm of 2, the base 2 logarithm of 3. And that gives us this number again. So, okay. Now, we need to calculate this entropy, or this conditional entropy, and this mutual information, and we can do that quite easily now. So we've got the entropy of A given B, and that's just equal to the mutual information of A and B minus minus the entropy of B, and we've calculated the entropy of B now. So the mutual information was 3.085, H of B was 1.585, so this gives us, 1.5. So this is exactly the same as the entropy of B given A. So things are extremely symmetric in this particular case. Okay, what about the mutual information here? Well, there we've got I, maybe I should write it up properly. So I, A comma B, that's for instance equal to, and then we can do it in various ways, but for instance we could take B and subtract the entropy from B given A, and that will give us 1.585 minus the 1.5 that we had, and that gives us 0.085. And there we go. So now we've completed everything to do with part A. We've found the entropies here, and we see that the mutual information, well, is rather low. In fact, it's quite low. So let's do the same thing for B. Now in part B, things aren't going to be quite as easy. We've figured out what one of these entropies is, but we have to figure out the rest as well. So let's do that. The entropy of A is, well, the sum of these functions. I could say AI, or the probability of AI would possibly be better, it's more precise. And so we just plug these values in, a half, a third, a sixth, into this function, and we add them together. So in other words, minus a half log 2 a half, minus a third log 2 a third, minus a sixth log 2 a sixth, and that gives us roughly around about 1.459. So it's a little less than this one here. And of course that's no surprise, because we have maximal entropy by the first source theorem when we have even distribution of probabilities. So, okay. Now, at this point we can calculate at least one more probability without doing a lot of work. And that's, for instance, the joint probability. So we have h a comma b, that's equal to h of a plus the probability, the joint the entropy of b given a. So that's equal to 1.459 plus 1.5, which gives us 2.959. So, and again we see that the entropy is slightly less down here than it was before. To find the remaining positions, we have to find the entropy of B. So let's do that. This time around we don't have exactly the same sort of symmetries that we could use in part A, but it's not too bad. So we need to find the entropy of B, and that's the sum of, well, this information function, P of B j, or in other words, the sum over the probabilities times their logarithm. So we need to find these probabilities. So let's do that. So for instance, P of B1, well, what's that? And now that we're down in part B, I should really change these probabilities as well to make them more relevant, like so. Now the probability of A1 is a half, and A3 is a sixth. So to get to B, we can either come from A1, A2 or A3. So in other words, this is the conditional probability that we get B1 given A1 times its probability, or in general AI times the conditional probability that we get to B1 given AI times the probability that we started in AI in the first place. So this is equal to, well, the conditional probability that we started in A1 and got to B1 was a half, that was the green line. The probability that we were in A1 in the first place, or that we sent that, was a half. Now for A2, there was a quarter chance of ending in B1, and there was a third chance of sending A2. And finally we have a quarter chance of getting from A3 to B1. And there's a sixth chance that we sent A3 in the first place. So this gives us 3/8. So B1 is equal to a third. Sorry, did I say a third? Yeah, B1 is equal to 3/8. Okay, what about B2? Well, it's very similar. The probability that we get to B2 is the probability that we started in A2 and then go from A1 to B2. So it's a quarter probability that we get this way times a half that we sent A1 in the first place. The next is to look at A2. So we have a half chance of getting from A2 to B2 and a third chance to send A2 in the first place. And then we have a quarter probability of getting from A3 to B2, and there's a sixth probability that we sent A3 in the first place, and that gives you a third. Okay, what about B3? Well, that's similar. How do we get to B3? Well, we could get from A with a quarter chance times the half probability of starting in A1 in the first place, or sending A1. And similarly, we have a quarter times a third chance of sending A2 and receiving B3. And then we've got a half probability times a sixth probability that we send A3 and receive B3, and all in all that gives you 7/24. So this is that function there of 3/8 plus the function of a third plus this function of 7/24, and that gives you roughly around about 1.577, which is what we then can write down here. 1.577. Okay, now we're nearly done with part B as well, because we can calculate some of the other numbers now. In fact, we should be able to calculate everything. Let's see. So, to calculate this conditional entropy, for instance, the entropy of A given B, we could, for instance, say, well, that's the entropy of A and B, or the joint entropy of A and B, minus the entropy of B, which we've now calculated. And that's, where was it? The joint entropy was 2.959, and the entropy of B was 1.577. So that gives us 1.382. So let's write that down, 1.382. The mutual information is also, it's also possible to calculate that. That's, for instance, if what we get by saying the entropy of, let's say, A, or maybe B, since we've just calculated that, B minus the entropy of B given A, and that gives us 1.577 minus 1.5, which we found in the beginning, and that's equal to 0.077. So that's the final number that we have here, and we are done. And you see here that the mutual information, so the amount of information that we can push through this channel is, well, it's not very big, but it's even smaller than what we began with. So, in part C, you're asked to guess what the maximal possible mutual information is. So how big can that get? So we've got something rather small and something even smaller. How big do you think these numbers can actually get? And that all relies on what sort of probabilities you start with. So I'll leave that to you to guess. That's for you to guess. So, have you guessed it? Well, let's see. Now we'll try to find the answer analytically. Now in the final part of the problem, we have to find the channel capacity. That's the maximal value of the mutual information here, which we found to be equal to 0.085 in the case where all the probabilities of A were the same. But in general, could it be any bigger than that? Well, that's what we're going to find out now. So we have to calculate the mutual information and then maximize it, and that'll depend on the probabilities of A1, 2 and 3. So I've written the probability of A as X, the probability of A2 as Y, and then the probability of A3 is going to be 1 minus those two probabilities. So, in order to do that, we can note that this is equal to the maximal value of the entropy of B minus the conditional entropy of B given A, and we know what that's equal to. That's still 2/3. So we just have to maximize the entropy of B and we're done. So let's do that. So first of all, to calculate the entropy of B, we just sum over the information, this function here, of all the probabilities of the B's, here Bj, so we're summing over those three. In order to find this, we need to calculate the probabilities of those elements, B1, 2 and 3, those symbols. So for instance, B1 has probability, well there we have to do like we did in part B, and see, well, how do we get to B1? We could get to B1 from A1, 2 or 3. So for instance, A1, the probability of getting from A1 to B1 is a half, and the probability of sending A1 in the first place is x. So that's a half x. We could have also got from A2 to B1, so that would have been with a quarter chance, times the probability that we sent A2 in the first place, which is y. And similarly, we've got a quarter chance of getting from A3 to B1, and then 1 minus x minus y, probability of having sent A3 in the first place. So if we tidy this up, we've got a half x minus a quarter x, that's a quarter x, so a quarter x, and then we've got 1 there, and the y's cancel out, so we're just left with a quarter 1 plus x. For B2, we have to get to B2 from these three symbols here, so we've got a quarter chance of getting from A1 to B2, and again we have probability x of sending A1. Then we have a half probability from getting from A2 to B2, and we've got y probability of sending A2, and then we've got a quarter times this last term again, and all that we've done here is just to change x and y around in these terms. So here we're just replacing x by a y. And finally, we have the probability of B3, that's just a quarter times x plus a quarter times y, plus now a half times 1 minus x minus y. And that gives you, if you calculate it, a quarter times, well here we've got a half, so that'll have to be 2. And minus x, minus half an x, where we've got a quarter x, that leaves you minus a quarter x. And the same for y, by symmetry again. And there we go. There are the three probabilities of B 1, 2 and 3. So if we then put them into this sum here, we get that that's equal to I of 1 plus x quarters plus I of 1 plus y quarters plus I of 2 minus x minus y quarters, and we are done. Well, we're done with that at least. So now we have to maximize this entropy here with respect to x and y. So what we do is we differentiate this HB. We could also differentiate the mutual information here by, well, if we differentiate that, we're differentiating this this term minus this term. This is a constant, so that'll just disappear when we differentiate it. So we can choose either way, but it doesn't really matter. So let's try to maximize this one here. For instance, by first differentiating in x, and we're setting this to be 0 to find a maximum, a local maximum. So that's d of dx of I of all of this, 1 plus x quarters plus d dx I 1 plus y quarters plus d dx of I 2 minus x minus y quarters. Now, if we differentiate this information this information function here, this one here, we get a pen that's running out. We get this function here. So we first differentiate x, that leaves us with minus log 2x, and then we differentiate the logarithm, and then we just get minus 1 over ln, or the natural logarithm of 2. We just get 1 over x, which divides out by x and leaves us with the natural logarithm factor. So that's sort of ugly, but it actually turns out not too bad here. When we're differentiating this term here, then, well, we get a quarter from the inner function there, times this differentiated, which was this here, minus log 2 of what we've got, 1 plus x quarters, minus the natural logarithm of 2. The middle term here doesn't contain anything to do with x, so it's just a constant with respect to x, so we have 0. And then again, here we have minus x divided by 4, so this is minus a quarter, times this function differentiated like so, and that gives you minus log 2 of the inner function here, 2 minus x minus y over 4, minus the natural logarithm inverted, and so forth. We see that these terms here, this constant term and this constant term, they just cancel out. And we're left with this mess. I'll just write it a little bit simpler as a quarter times, well, minus a quarter log 1 plus x over 4. And then minus minus gives us a quarter log 2 minus x minus y. And there we go. Okay, it looks a bit messy, but it's not too bad, because all of this was equal to 0. So we have that this term here is the negative of this term, and there's in fact a minus in front. So that gives us that we have a quarter log 2 1 plus x over 4, and that's equal to a quarter log 2 minus x minus y over 4. And you can see we can cancel the quarters, we can cancel the logarithm, so to speak, by raising, by letting this be the exponent of 2. And then we cancel the 4's here, and we're left with 1 plus x is equal to 2 minus x minus y. And finally, if we collect the x and y terms, we have 2x plus y is equal to 2 minus 1, which is 1. Okay, that was a lot of work just to get that equation, that fact there. So I'll just write it over there, over here. So 2x plus y is equal to 1 was the conclusion. Now, that's if we differentiated by x. But this expression here that we're differentiating, if you look at it, it's symmetric with respect to x and y. So if we instead differentiate it with respect to y, then all we do is change all the x and y's around, And the conclusion will then be the same here, except that we are swapping x and y around. So we can conclude that this is true. We have that 2x plus y is equal to 1. And we have what happens if we have that 2y plus x is equal to 1. And now we just have to figure out what x and y are equal to. So we have two linear equations in two variables. So you could, for instance, add these two together. Then you get 3x plus y is equal to 2. So that gives you that x plus y is equal to 2/3. And then if you subtract that equation from the first one, for instance, then the y's disappear. And that leaves you with x being equal to 1/3. And again, the symmetry between x and y. So y is also equal to 1/3. And apparently, the third probability there, 1 minus x minus y, is also equal to 1/3. So we get that, well, let's just write it up there. 1 minus x minus y is equal to 1/3. So, in fact, all of the probabilities of A are equal to 1/3. And we calculated what the mutual information was in that case. That was, in fact, in part A, where we had these probabilities, and it was equal to 0.085. So that's, in fact, what our capacity is going to be. So roughly about 0.085. And sorry, I'll just write this a little more legibly. So there we go. And we've got that PAI is equal to 1/3. So, so if you guess that the mutual information was greatest in this value here that we calculated when the probabilities of the A1, 2 and 3 were all the same, that was the maximal possible mutual information, well, then you were right. And in fact, that's the channel capacity. So that's how much information can flow through this channel optimally, or best possible. So I think we have covered everything in this question now. So thank you very much.